And welcome, ladies and gentlemen. Mr. Cowan here helping you with graphing linear inequalities, Chapter 12, Lesson 9. Goal for today, graph a linear inequality on the coordinate plane. Now think about where we've been. We've been graphing linear equations. Now it's time to move on to linear inequalities. We've also been talking about slope. We've talked about solution. I should mention solution. Remember, solution is any number or numbers that makes a statement true. So our goal today is to be able to look at something like this, not just see a starting value, not just see a slope, but to actually show all the solution or solutions to a linear inequality. In other words, where before we could write an equation or take an equation and graph it, today our focus is going to be taking a linear equality and graphing all the solutions. All right, pause for a second. Go ahead and write whatever the date, whatever the assignment number is. Come on back when you're ready. So on to notes, ladies and gents. Want to bring you back, a little walk down memory lane. First things first, equations with an equal sign. In this case, I'd like you to notice that as we solve, we find the solution that is 4. There's only one variable here. And in fact, in this case, there's only one number that would make this statement true. The only number that would make this statement true is, you guessed it, 4. If you went and multiplied by 2, you get 8. 8 plus 3 is 11. True or false, 11 equals 11. If you tried any other number, 14, 44, negative 44 million, it would not work. The only number that makes a solution is 4. On the other hand, look what happens now when you go to an inequality. Now there's still only one variable, I only see an x. But when we solve this, this statement says, look, any number that is 4 or larger will be true. Now there's infinitely many solutions that would make this statement true. Think about it. If I put a number in, substitute a number in, maybe I substitute, well, 4 would work, but let's try 5. 2 times 5 is 10. 10 plus 3 is 13, which of course is true. What if we tried 50? 2 times 50 is 100. 100 plus 3 would be 103. And it's still true. In fact, there are so many numbers that would work. P.S. If you tried 6 or negative 2, that of course would make a false statement. Think about this. 2 times negative 2, negative 4. Negative 4 plus 3 is negative 1. That's not correct. Which, by the way, is why we don't graph or color in any of the numbers to the left of, why did I write 8 there and 4? How about that? I bet that should be 4, huh? Point here is, equations often have one variable, one solution. Inequalities, one variable, infinitely many solutions. But now we go back to equation, but in this case, there are 2 variables. Y is equal to 2 times some x input, add 3. Now, oftentimes we start with 0, we'll put in a few other input values, 1, negative 1, 2, but I just want to point out, you could go on and on and on forever in both directions. Furthermore, you could choose any decimal or fraction in between these numbers. And since there are billions and billions and billions and billions of points, and really that's just the beginning, this equation also has infinitely many solutions. There are an unknown number, an infinite number of solutions, x value and y value, that would make this statement true. Okay, so onward we go. What's next? Well, next is replacing that equal sign with an inequality sign. There are 2 variables here. We see a y and an x, but what on earth does this mean? How many solutions are there, and how would we plot those solutions on a coordinate plane? That's our goal. Let's go exploring, shall we? All right, so we see the line as if there were an equal sign. All these points would be true. But this mathematical statement says, yes, it can be equal, but it can also be greater. So we're going to pick some points. And perhaps not surprising, you guys know my affinity for 0. Let's try the origin. Let's substitute in 0 for x and 0 for y, and let's see what we get. 2 times 0 is 0. And if we add 0 and 3, we get 3. True or false, 0 is greater than or equal to 3? No, 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 no. That doesn't work. Let's try another point, just for kicks, something down here in the fourth quadrant. So let's try the point 5 when x is 5 and y is -2. I'm going to put a little question mark up here. So 2 times 5 is 10, 10 plus 3 is 13, and we still have a false statement. So let's go to the other side of the line, shall we? Let's try x is -3 and y is 0. So we'll substitute in -3 and 0. And let's put a little question mark here. Is this a true or false statement? 2 times -3, -6. -6 plus 3 is -3. Ah, hello. 0 is in fact greater than -3. This one's true. Put a little dot there and we'll leave it. We won't cross it off. Let's try something else then. Let's try -5, +6. So when x is -5 and y is 6, let's see, is this true or false? Let's see, -10. -10 plus 3 is -7. And once again, we get a statement that is clearly true. I'm kind of seeing a pattern here. So let me continue with other points. I'm going to do something down here in the third quadrant. If x is -6 and y is -4, -2 times -6 is -12, plus 3 is -9. And again, we get a true statement. Let's try another one, shall we? Let's try 0, 6. Why not? When x is 0 and y is 6, in this case, 2 times 0 is 0, add 3, and we get true again. Okay, this is kind of weird. Let me do a couple of other points now. Let me go back to the other side of the line. I'm going to try 5, 3. When x is 5 and y is 3, 2 times 5 is 10. 10 plus 3 is 13. Nope, nope, nope. That's false. All right, forget that. Let's try -1, -3. So when x is -1 and y is -3. 2 times -1 is -2, plus 3 is +1, and that is still a false statement. So why did you do extra points? Well, as you can imagine, none of these points over here would work. If I tried 3, 0, if I tried 3, 3, if I tried 3, 6, if I tried 3, -4, if I tried -3, -6, or -3, -600, none of those points over on that side are going to work. On the other hand, if I were to try -3, 1, or -3, 2, or -3, 3, or -3, 4, or -3, 4 trillion, or any of these points right here, or any of these points right here, or any of these points right here, they're all going to be true statements. And folks, how should we then color in millions and millions and billions of dots? Well, I'll tell you what, I'm just going to grab my highlighter, colored pencil, crayon would work at home, or you can use your pencil. If you shade well, shade lightly. But here's the point. There are still going to be infinitely many solutions. How do you graph or represent those solutions? Instead of sitting there and drawing an infinite number of points, we are simply going to shade in the area that represents all those solutions. Now, that was a lot for one page. I, in fact, wish I would have done the false all in red to show you that none of these points work on this side, but all of them work on the other side. Pause if you need, rewind, come back when you're ready to move on. All right, so your turn. Now we're going to try these. And if might be no surprise, I'm going to always recommend substituting in the origin. It is almost always the best point to put in, the quickest point, the most efficient point to check. However, there will be a time when using the origin won't help you decide which shade, which area of the coordinate plane to shade in. I want you to keep that in mind. When is going to be a time where 0, 0 is not going to be a good idea? Meanwhile, let's go. Substitute in 0. Go ahead and compute. True or false? Yep. And as you can imagine, because this is true, so is that, and 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 all the points on this side. So we're going to go ahead, I should have got my highlighter out and shade that in. Meanwhile, if you insisted on trying some point on the other side, say 6, 0, so when y is 0 and x is 6, as you can tell, it's going to be a false statement. So I'll always encourage you to check at least one point. Notice the word at least. If you want to check a point on both sides, it's probably a good idea. All right, onward. Let's try 0, 0 here. Substitute in 0 for x and 0 for y. And let's check. This is true. Okay. Once again, this side is going to work. So I'm going to go ahead. I'm going to color in everything over there because there are infinitely many points that would make this statement true. If you insisted, you could try -6 for a y value, +6 for an x value. Excuse me. Yeah, that works. -6 for a y value, +6 for an x value. -6 is less than or equal to 2. Huh. That's true. What did I do wrong here? Oh, wake up, Mr. Callan. 0 is not less than -4. Look at that. Even teachers make mistakes. So you can see that checking a point on both sides is a wise idea. Hey, guess what? 0 is not less than -4, so the origin does not work. And as you could see, I wish I wouldn't have erased it. I tried the point when x was +6 and y is -6, and that one was true, which means if I were to shade correctly all the solutions to this, they're all going to be down here. All right, so you'll probably see me check myself further on. Let's try 0, 0. Let's try this point right here, substituting in 0 for x and y. -3 times 0 is 0, plus 1 is 1. True or false, 0 is less than 1. Okay. Now, before I even shade it, I'm going to go to the other side. Let's try 4, 1. So when y is 1 and x is 4, let's check it. -3 times 4 is -12, plus 1, go up 1, -11, but that is most definitely false. So that gives us further evidence, further justification that all the solutions in this particular inequality will be over in this region. And let's try it again. Should we shade up? Should we shade down? In this case, -2 times 0 is 0, plus 4 is 4, and that's false. So let's not shade that one in. Let's try something else. Let's try -6, -1. So we'll substitute in -1. -2 times -6 is 12. +12 plus 4 is 16. True or false? What'd you do, Mr. Callan? Hold the phone, folks. I'll be right back. All right, folks, I figured it out, and the problem was that the line was graphed incorrectly. Here we go with +4 right here, which means the y-intercept should be here. And yes, -2 to 1. But please notice now that both of those points that I tried are on the same side in the same region compared to that line. So I'm going to kind of squiggle that out. So it is no wonder that 0, 0 and negative 6, 1 did not work. Let's go ahead and try a point on the other side of this. Let's try when y is positive 4 and x is positive 6. Now, if we were to work this out, negative 2 times 6, negative 12. Negative 12 plus 4, negative 8. Is 4 greater than or equal to negative 8? You betcha! Which means now that we've checked points on both sides of the line, we found 2 that don't work, 1 that does, so we're going to shade up and above. All right. Apologies for the couple mistakes, but that's why it might be a good idea to check more than one point. I myself will always check 0, 0, except with an exception. We'll see if you can figure that exception out in a minute. Pause, rewind, re-listen if you need. Otherwise, let's go on. Now, there will be a time when we will use a solid line, and there will also be a time when we'll use a dashed line. The question is, when will we use each? So let's explore this. Both of these have an inequality symbol of greater than. So it might come as no surprise that they will share a region of solutions. My question is, will the points directly on the line itself work? So let's try 0, 3 when x is 0, y is 3. Let's try negative 4, negative 5 when x is negative 4, y is negative 5. In this case, 3 is greater than or equal to 2 times 0 is 0 plus 3 is 3. Well, because it's or equal to, this is a true statement. Is 3 greater than 3? No, but is 3 equal to 3? Yes. Check this one out. Negative 2 times negative 4, negative 8 plus 3 is negative 5. Aha, because it can equal it. Therefore, all these numbers on the line will be solutions. If they're all solutions, instead of drawing billions and billions and billions of points, that's when we're going to draw a solid line. All right, but let's check this next one out. Now, just for kicks, I could try 0, 3 again. 2 times 0 is 0, plus 3 is 3. Now, wait a second. This is a false statement. 3 is not, in fact, greater than itself. Now, I could try negative 4, negative 5 again, but let's try something else, shall we? Let's try negative 2, negative 1. So I'm going to substitute negative 2 for x, negative 1 for y. 2 times negative 2, negative 4, plus 3 is well, there we go again. That is not true as well. And as you might imagine, all the points on the line, including all the little points in the middle, will not work. So in essence, they don't work, but everything above and to the left does. We need a boundary showing, look, these points don't work, but everything to the left, everything above does. Ladies and gents, that is why we use a solid line versus a dashed line, excuse me. So use a solid line if the lines make the algebraic statement true. As an example, I would say greater than or equal to, less than or equal to. It's all about that equal piece. On the other hand, use a dashed line if the line's points make the algebraic statement false. That would be a less than or a greater than. Folks, we finished exploring. Now let's try some examples. If you'd like, pause, do this on your own. For the rest of us, let's go one at a time. First things first, I see a dashed line because it must be less. It cannot be equal. I'm going to put 1 over 1 here as my slope. My starting value is 4. So 1, 2, 3, 4. And then if I go up 1 and right 1, or down 1 and left 1. Now the key here is I can't draw a solid line, so I'm going to make sure I draw nice, loud, and clear that these are dashes. All right, now it's time to check. You know Mr. Callan, I'm going to check 0, 0. In this case, 0 is in fact less than 4. Because 0 works, so 2 should all the points that are down below. But you've seen Mr. Callan make mistakes before, so ever so quickly, I'm going to check another point. Let's check -6, +6. 6 for the y value, -6 for the x value, -6 plus 4. And last I checked, +6 is certainly not less than -2. Onward we go. I see a solid line because it can equal all those points. Starting value of -2. Slope is +1 to +2, so I'm going to go up 1 and right 2, and up 1 and right 2, and I'm going to do so repeatedly. Of course, you could go down and left and still have a positive slope. And again, all those points do in fact make solutions. So instead of drawing an infinite number of points, I'm going to represent those points with a line. And now I'm going to check. I'm going to check 0, 0 again. Let's substitute 0 in for y and 0 in for x. Half of 0 is 0, minus 2. Aha, this appears to be a true statement. So I'm going to go ahead. Well, let me check it first, shall we? Let's check a point. So 0, 0 works. Let's try something down below, shall we? Let's try +3, -5. Substituting in -5 for the y value. You know what? I'm going to try +4 because that'll make an easier set to compute. Half of 4 is 2. 2 minus 2 is 0. True or false? False again. So because that side should not work and the other side should, I'm going to go ahead and shade in the region that represents all the solutions to this inequality. One last one to do, ladies and gents. Oh, interesting. Starting value is 0, slope -3 to 1, so I'm going to fall 3 and go to the right one. Naturally, you could also increase 3 and go to the left one, up 3 left one, up 3 left one, up 3 left one. Oh, solid line, because those can equal. Wait a second. Once upon a time, I asked you a question. When would 0, 0 not be a good choice to use? Well, in this case, we already knew that was true because of the or equal to sign. 0, 0 is directly on the line. So that doesn't really help us find a region to shade. Therefore, I'm going to pick one on a single side. Let's go with -4, +2, shall we? So let's substitute in -4, excuse me, -4 for the x value, +2 for the y value, and let's find out, shall we? -3 times -4, the opposite of a negative, is positive. Hey, this one's true. Meanwhile, we're going to check the other side just to make sure. I'm going to try 6, 0, substituting in 0 for y and 6 for x. We get a statement that is certainly false, which verifies that all the solutions to this linear inequality are going to be over here, below, and left. Ladies and gents, to summarize just a couple points we've talked about. Know when to use a solid line if it makes the statement true because of the or equals, versus when to use a dashed line if it makes the statement false because it cannot be equal. And may I suggest always using the origin, unless of course the origin doesn't work. Hint, if you're like Mr. Callan and make mistakes, try 2 points, one on each side. Folks, that's what I have for you. Head into your homework, take care, and do well. Let's grow, ladies and gentlemen.